Hey everyone, ready for a real head scratcher today? We're diving into quantum entanglement, where particles get all linked up across ridiculous distances, like light years apart, and somehow mess with one, the other reacts instantly. It's like they're having a secret chat across the universe.
Yeah, it does sound like something straight out of Star Trek, doesn't it? Spooky action at a distance, as Einstein called it.
Spooky is right. So we're tackling a research paper on this, and it gets pretty wild, talking about holographic theory as a possible explanation.
And to even start unpacking that, we've got to make sure we're all on the same page about why quantum entanglement is such a brain bender.
Right, because it's not just that they influence each other, it's the how, right? Like faster than light somehow.
It's the correlations. They're stronger and way faster than anything classical physics can explain. Imagine flipping two coins.
They land randomly, heads or tails, 50-50.
Now, with entangled particles, it's like those coins are linked. Flip one heads, the other goes tails instantly, no matter how far apart. It's as if they're coordinating without any physical connection.
Okay, yeah, now it's spooky. That seems to break, like, the fundamental rules of physics, doesn't it?
You're hitting the nail on the head. One of the bedrock principles of physics is that nothing, not even information, travels faster than light. Entanglement seems to throw that out the window.
So how do we even begin to explain it? Is that where this whole holographic universe idea comes in?
That's one way to tackle it. But before we get there, we have to address Bell's theorem. It's crucial for understanding why entanglement is so groundbreaking.
Bell's theorem. That name rings a bell, but refresh my memory.
It's a bit technical, but essentially it gave us a way to test if these correlations, these spooky links, could be explained by something we just hadn't discovered yet, like some hidden variable we couldn't see. Turns out that's not it.
So it's not just missing information, it's something totally different about how the quantum world works.
Exactly. And that's where holographic theory comes in. It tries to make sense of these bizarre quantum rules. Now, imagine a hologram, like on a credit card.
Yeah, those shiny 3D images printed on a flat surface.
Precisely. Holographic theory suggests our entire universe might be like a giant version of food. That all the information about our 3D reality might actually be encoded on a distant 2D surface.
Hold on, so you're saying our 3D world is like an illusion projected from some flat screen far, far away. That's even weirder than these particles whispering to each other.
It's a mind-bending concept, but that's the gist. And here's where it gets even more interesting. Some physicists think those entangled particles, they might be connected by tiny, invisible wormholes on this holographic surface.
Wormholes? Like portals to other dimensions? Are we going full sci-fi here?
Not quite portals in the way you'd imagine. Think of them more like shortcuts or tunnels through the fabric of space-time. These theoretical wormholes could allow entangled particles to communicate instantly, regardless of the distance between them in our 3D world.
So if I'm following, holographic theory says our universe is like a movie projected from somewhere else, and these entangled particles have found a way to sneak behind the scenes and chat through these little wormhole shortcuts.
That's a pretty good analogy. It's all very complex, and physicists are still figuring out the details, but this idea of our reality as a holographic projection is a huge area of research with potentially massive implications.
Okay, my brain needs a break to process all of this, but this is where things get really wild, right? Black holes come into play. Black holes, yeah, those things give me the chills, but I'm ready for more. Lay it on me.
Black holes are like the ultimate cosmic laboratories. They push physics to its limits, really make you question everything we think we know.
Okay, I'm hooked. You mentioned this thing called the black hole information paradox.
Yeah.
What's the connection to this holographic universe idea?
Well, black holes, they're famous for sucking up anything that gets too close. Stars, planets, even light itself. Once something crosses the event horizon, that point of no return, it's gone.
Yeah, like a cosmic vacuum cleaner, nothing can escape.
Exactly. But here's where it gets weird. Physics says information can't be truly destroyed. Think of it like ripping up a piece of paper. It's gone. But the information, the arrangement of the atoms, still exists.
So even if a black hole swallows, like all my embarrassing childhood photos, the information is still out there somewhere, just scattered.
In a way, yes. But then, if black holes are trapping information forever, wouldn't that break the laws of physics? This is where holographic theory swoops in. It suggests that the information isn't lost inside, but rather encoded on the surface, that event horizon itself.
Encoded, like it's plastered on the surface, cosmic graffiti on the black hole.
Well, maybe not graffiti, but I like the way you think. Imagine the surface of the black hole as a ridiculously complex, ever-changing hologram. As stuff falls in, it gets imprinted on this surface, becoming part of the hologram.
Whoa, so not gone, just transformed into something we don't get yet. Okay, but if they're holding onto this information, what happens when black holes evaporate?
Yeah,
Because I thought they do eventually.
you're right, they're not immortal. Hunking radiation makes them shrink and eventually disappear.
Yeah.
And that's where the page curve comes in. It's key to understanding what might happen to that hoarded information.
Page curve sounds intense, like a graph of doom for information or something.
Not quite. Imagine a graph that shows how much information a black hole can hold as it shrinks. At first, you'd think, less black hole, less information, right? Like it's disappearing. But the page curve throws a curveball.
Okay, you gotta tell me, what does it say?
It suggests that as the black hole shrinks, the amount of information it holds does go down at first, but then it hits a point and starts releasing that information back out into the universe, a cosmic exhale.
So it's not a one-way trip for information after all, it gets a round-trip ticket?
Exactly. This page curve, backed up by some seriously intense math, suggests that information eventually escapes, though it might be scrambled, like trying to put a shredded document back together. And holographic theory fits in by saying that information was never truly inside to begin with, always on that surface.
So the information gets a round trip, that's a relief. But how do we even study something as mind-boggling as a black hole? It's not like we can just go on a field trip to the edge of one.
You're right. They're a bit hard to wrangle for research, to say the least.
Mm-hmm.
But physicists are finding ways, developing incredible new tools.
Like what? What are they using to unlock these secrets? Give us the inside scoop.
Well, quantum computers are playing a huge role. Remember how information might be encoded on the surface of a black hole? Quantum computers could be the key to simulating and understanding that process right here on Earth.
Whoa, miniature black holes in the lab? That's both amazing and kind of scary.
Not quite miniature black holes, at least not yet. But it's still groundbreaking stuff. They're creating simplified models of these incredibly complex systems, testing out the predictions of holographic theory in a controlled way.
You mentioned a Google experiment before, something about a simulated wormhole. What was that all about?
Ah, yes. The Google Sycamore quantum processor experiment. It wasn't a traversable wormhole like you see in the movies, but they simulated the key properties, observed how information behaved within that simulated environment.
Okay, that's just mind-blowingly cool. But as much as I love the idea of us cracking the code of the universe with these quantum computers, there have got to be challenges. What are some of the limitations of this whole holographic theory?
You're right to ask that. It's definitely not a walk in the park. It's still early days for this theory, and one of the biggest hurdles is just the sheer mathematical complexity of it all. We're pushing the boundaries of what we understand about physics, so even coming up with the math to describe and test it is a massive task.
It's like trying to assemble a puzzle where half the pieces are missing and we don't even know what the picture's supposed to be.
That's a great analogy. And on top of that, designing experiments to directly test this theory is incredibly difficult. We can't exactly create black holes in a lab or take a quick trip to the edge of one.
Yeah, I'm good on the black hole trips. I prefer my information intact, thank you very much. But even if we're a long way off from fully understanding holographic theory, the potential payoffs seem massive. You said it could impact fields beyond physics too, right?
Absolutely. The coolest thing about fundamental research like this is that it can have ripple effects we never expected. For example, the holographic principle that underlies all this has sparked some really cool ideas in computer science, especially for data storage and processing.
So instead of cramming more transistors onto a chip, we might be storing information holographically one day, like a universe on a credit card.
That's the idea. Holographic data storage could let us store insane amounts of information in a fraction of the space. And it's not just storage. This theory could revolutionize how we understand materials, lead to totally new technologies we can't even imagine yet.
It's mind-blowing to think that these cosmic mysteries, black holes, entangled particles could lead to breakthroughs that impact our everyday lives here on Earth. So for our listeners who are now just as hooked on this as I am, what's the big takeaway? What should we be pondering as we go about our day?
I think the most important thing to remember is that the universe is far weirder and more interconnected than we tend to think. Quantum entanglement, black holes, this holographic theory, they're not just concepts in a textbook, they're glimpses into the fundamental nature of reality itself. Every discovery, every theory we develop brings us closer to unraveling these cosmic mysteries.
It really makes you feel small, in a good way, you know? Like, with all our knowledge, we're still just scratching the surface of understanding the universe. And who knows what mind-blowing discoveries are waiting for us out there. That's what's so exciting about science. There's always something new to uncover, a new layer to explore.
Exactly. It's that sense of wonder, that drive to explore the unknown that keeps it all so captivating.
Well said. A huge thank you to all our listeners for joining us on this wild ride through quantum entanglement and holographic theory. We hope you're leaving with more questions than answers and a renewed sense of awe for this incredible universe we call home. Until next time, keep those minds curious and never stop exploring.